So starting with D and F block elements. So D and F block elements, they are called as transition elements. D block elements are called as transition elements and F block elements are called as inner transition elements. Now inner transition elements, they contain two groups. They are grouped into two series called lanthanoid series and actinoid series. Lanthanoid series, it starts from lanthanium, and actinoid series starts from actinium. Lanthanium atomic number is 57 and actinium atomic number is 89. So altogether these two series, that is your lanthanoids and actinoid series, it comes under inner transition elements, which is coming under F block. F block we can say that, and D block is your transition elements. We have got 4 transition series in the D block elements. So why it is called D block? Because D block elements show a transitional behavior between the two. Between the two means between highly electropositive S block and weakly electropositive P block, or we can say highly electronegative P block also, we can say that. What I said, D block elements show a transitional behavior. Transition means a behavior in between, it lies between highly electropositive S block and highly electronegative P block elements. For that reason, these elements are referred to as transition elements. So now we have got, as I said we have got in D block, there is 4 transition series. There is, first is your 3D series. This series, what you can find is that it starts from atomic number 21, that is scandium, to atomic number 30, that is zinc. Altogether 10 elements in the 4th period. Similarly, second transition series starts, that is your 4D series, starts from atomic number 39, we can say that, and it ends in atomic number 48, we can say that. Got it? That is atomic number 39 to atomic number 48. Again same thing, cadmium atomic number 48 is. So now next is we have got 10 elements here also in the 5th period, and third transition series and 4th transition series, that is 5D and 6D series. Got it? So that is 5D series starts from what you can say lanthanium. Got it? And it's up to, that is hafnium to mercury, that is 80, we can say that atomic number. This belongs to 6th period, and 4th transition series in the 7th period, that is actinium 89, and it goes to 104 and above, we can say that. So in this way we have got the introduction of the transition and the inner transition elements, which I gave it to you. Now we'll come to the definition of the transition element. Transition elements are those elements which possess incompletely filled d orbitals in the ground state or in their ions existing in chemically significant oxidation state. You can see in your screen that transition element is defined as element whose atom in the ground state or ion in one of the common oxidation states is incompletely filled d subshell, we can say that, incompletely filled d subshell. Got it? Clear? Again I repeat, transition elements we can say in this way also. Transition elements are those elements which possess incompletely filled d orbitals in the ground state, alright, or in their ions existing in chemically significant oxidation state, which I have written it the same manner on the screen. You can read it out. Clear? So now except copper and zinc, all other elements have partly filled d orbitals in their elementary form in the ground state and the true transition elements, except copper and zinc, we can say that. Now zinc cannot be regarded as a transition element. Not only zinc, cadmium and mercury, that is they are not regarded as transition elements. Why? The reason is that in the true sense they possess completely filled d orbitals in their elementary state form as well as in their common existing ions. Completely filled d orbitals. What was my definition of D block? The definition was which has got incompletely filled d orbitals in the ground state, but zinc, cadmium and mercury have got completely filled d orbitals in their elementary form as well as in their common existing ions, we can say that, commonly existing ions. In fact, zinc, cadmium and mercury do not exhibit, listen carefully, zinc, cadmium and mercury do not exhibit the general characteristic properties of the transition elements and behave quite differently from the rest of the elements belonging to the D block of the periodic table. Alright, their behavior is quite different. We will study it later on in the chapter. We will be studying it. Alright, so you can see it on the screen. It is being already given there that zinc, cadmium, mercury's exceptional behavior as compared to other members of the respective series. It has much higher atomic radius and ionization enthalpy. Its compounds are white while those of the other members are colored. We can say that. Clear? While those of the other members are colored, we can see. So hence, due to these two reasons also we can say, and some more reasons we will be studying it later on in the chapter. You will be studying it. You will see that these elements are not considered, zinc, cadmium and mercury are not considered as transition elements even if they belong to the transition series. Even if it comes under the D block, even if it comes under the transition series, we can say that. So then what are the characteristics, general characteristics of the transition elements? What we find? The general characteristics is that in general the atomic radii of transition elements belonging to a particular series decreases with increase in atomic number. The decrease becomes small after midway. Alright, the decrease becomes small after midway. The atomic radii of transition elements that is belonging to a particular series decreases with increase in atomic number. We can say that. Clear? This is why the atomic radii remains almost constant after midway in each series. Near the end of each series, there is slight increase in the atomic radii. There is a slight increase in the atomic radii in the why? Because as the atomic radii is what you can say, the subshell is fully filled, like zinc, cadmium, mercury, the subshell is fully filled. So what you find is that there is, as the subshell is fully filled, the electrons are going to repel one another. So hence there is a slight increase in the atomic number. Atomic radii. There is a slight increase. The reason is that. So hence I said that near the end of each series there is a slight increase in the atomic radii. You can say that there is a force of repulsion among the electrons which is being present at the end of the series as it is being fully filled. Alright. The atomic radii of transition elements increases on moving down the group. However, the atomic radii of the elements of second and third transition series are nearly the same. They are nearly the same. The atomic radii of the third second and third transition series. Why? The reason is the almost similar value of atomic radii of the elements of second and third transition series are due to lanthanoid contraction. Which we'll be again studying later on, that is under lanthanoids and actinoids when I'll be teaching you on our inner transition elements in F block. Then I'll tell you in details about it. What is lanthanoid contraction? Alright. Now, next is if you see the ionic radii, then transition metals exhibit various that is oxidation states. The radii of the ions are different in different oxidation states. The radii of the ions are different in different oxidation state. In general, the ionic radii decreases with increase in the oxidation state. We can say that. You note this particular point. It's very important. The ionic radii decreases with increase in the oxidation state. Got it? For the same oxidation state, the ionic radii generally decrease with increase in the nuclear charge. The decrease in the decreases with increase in the nuclear charge. That's the reason. Got it? The nuclear charge, as you have seen it, when you move from left to right across a period, the atomic size decreases. Why? Because there is an increase in the nuclear charge. Here also same thing. The gradual decrease in ionic radii in going from Ti2 plus ion to Cu2 plus ion is due to an increase in the effective nuclear charge, as I said you already. The ionic radii of the transition elements are smaller than those of the representative elements of the same period. Alright. Now, if you see the metallic properties, I am discussing with you the general characteristics of the transition elements. Alright. So, listen carefully. The metallic properties, if you see, but before metallic properties, one thing I want to share you of zinc, cadmium, mercury is that the elements with the exception of zinc, cadmium, mercury are very hard and possess low volatility. Again I repeat, before going to the metallic properties, let me say you that the elements with exception of zinc, cadmium and mercury, leaving behind zinc, cadmium, mercury, all these elements are very hard and they possess low volatility. We can say that. The metallic character of the transition elements may be attributed to the low ionization energy, we can say that, and the presence of several vacant orbitals in the outermost shell. Alright, due to the presence of vacant orbitals in the outermost shell and due to the low ionization energy, we have got a metallic character. The hardness of these metals indicates the presence of covalent bonds in them. Listen carefully. The hardness of these metals indicates the presence of covalent bonds in them. This may be possible due to the presence of unpaired d electrons in them. The d orbitals containing unpaired electrons may overlap to form covalent bond. Got it? May overlap to form covalent bond. So higher the number of unpaired electron present, more is the number of covalent bond formed by it, and greater is the strength of the hardness of the metal. I hope it's clear. Hence, transition elements exhibit metallic properties and are quite hard. It appears that both metallic and covalent bonding exist together in these elements. Got it? Now, due to this reason, what you find is that the densities of the the transition elements increase on moving from left to right in a series. We can say that on moving from left to right. Why? Because the atomic radii and hence the atomic volume decreases, whereas the atomic mass increases, due to which the density of the transition elements increases on moving from left to right in a series. If you see the melting and the boiling points of the transition elements, metals are very high as compared to those of the what you can say representative elements. We'll see a graph for it, not this one. We'll see a graph. So you can see here this particular graph as you can see. So before that, I'll just tell you the transition elements, they have got a very high melting and boiling points. Alright, the melting points of the transition elements rise to a maximum and then fall as the atomic number increases. Manganese and technetium have abnormally low melting points. Alright, abnormally, that is low melting points. Now I'll give the reason. Now see, you just see the graph here. You can see in the graph, that is manganese and technetium, they have abnormally, there is a low melting point. You can see in the graph, that is manganese shown in the dotted line and technetium also in the dotted line but in purple color, and manganese in the red color. You can see it very clearly. The high melting and boiling points of the transition metals are due to their close packed structure. Now listen the reason why it is having, that is transition metals having high what you can say melting and boiling point as compared to the representative elements. So you can also see the melting point first increase. You can see there in every graph the melting point increases. Alright, attains a maximum value. You can see a maximum value in case of chromium in the red dotted one, in case of molybdenum in the purple dotted one, in case of tungsten, that is W, in the green solid line. You can see that that's maximum value, you can see. So what I said you, that is the melting point first increase, attain a maximum value and then steadily decrease. You can see the graph is coming down in all the cases. The graph comes down in all the cases, steadily decrease as the atomic number increases. Got it? I hope you understood the graph. First it increases, attains a maximum value and then steadily decreases as the atomic number increases. You can see that. Now why? What is the reason behind it? Listen carefully. The high melting and boiling points of the transition metals are due to their close packed structure. Just now I said you. In this structure, the transition metal atoms are held together by strong metallic bonds which have considerable covalent character. Just now I said, they have got covalent character due to the presence of unpaired electrons because the overlapping takes place. Therefore, it requires a considerable amount of energy to break the metallic bonds in order to melt the metal. Consequently, these metals have very high melting and boiling points for that reason. What I said, it requires a considerable amount of energy to break the metallic bonds. Metallic bonds is formed. To break this metallic bonds, a huge amount of energy is required. A large amount of energy is required. Due to this reason, they have got high melting and boiling points. So already I said you, greater the number of unpaired electrons, stronger is the metallic bonding. Stronger is the metallic bonding. You can say that. Now, the question is that why it decreases? Because as atomic number increases in every series, the number of unpaired electron decreases. Alright, so as you move from D1, D2, D3, D4, D5. So D5 means all are unpaired. D6 onwards, again the pairing starts. So the strength of the covalent bond decreases, but atomic number is increasing. Atomic number is increasing. D6, D7 means atomic number is increasing. So the strength of the covalent bond decreases. For that reason, you can see there is a sharp decrease. There is a gradual decrease. Not sharp decrease, there is a gradual decrease. Got it? In melting and boiling points with the increase in atomic number. I hope you understood this. Zinc, cadmium and mercury have no unpaired electron. This is why these metals are soft and have low melting and boiling points. You can see zinc, cadmium, mercury at the bottom there. Got it? So at the bottom there you can see there. So in this way, in the graph you can see. So in this way they have mercury is a liquid at room temperature and has a melting point of around 200 Kelvin or 230 Kelvin around, we can say that. The unexpectedly lower melting point of manganese and technetium. I have said you in the beginning, manganese and technetium have low melting point. So why? This is probably due to their complicated lattice structures. This is probably due to the complicated lattice structure. Lattice means definite geometrical structure. That is a typical lattice structure, solid structure. So the maxima at about the middle of each series indicates that one unpaired electron per d orbital is favorable for strong interatomic interaction. We can say that. Clear? So in this way, you have understood why it has got a higher melting point in the middle, and then after that why it decreases the melting point. We can say that. Clear? Now after that we will see that as we move along a transition series from left to right, the atomic radii decreases due to increase in nuclear charge. We know that. Hence the atomic volume decreases. At the same time atomic mass increases, density decreases, just now I said you. So iridium has the highest density, scandium has the lowest density, where osmium has slightly lesser density than iridium, and osmium and iridium have almost the same density. Got it? Now coming to the ionization enthalpy. Now before moving to the ionization enthalpy, I will say you about little bit about ionization, about enthalpy of atomization. The transition elements in general exhibit higher enthalpies of atomization. The higher value of enthalpy of atomization of transition elements may be attributed to the presence of a large number of unpaired electrons in their atoms. Large number of unpaired electrons in their atoms. We can say that. Alright. Due to this reason, they have got high enthalpy of atomization. We can say that. Now coming to the ionization enthalpies, we can say that ionization energy. The first ionization energy you can see on a screen. The first ionization enthalpy of d block elements lie between s block and p block elements. They are higher than those of the s block elements and lesser than those of the p block elements. Already we have seen it. For that reason they are called as transition, because already I have said you the properties lies in between those of s block and p block. The first ionization enthalpy of zinc, cadmium and mercury are however very high because of their fully filled d subshell, that is n-1, d10 and ns2 configuration. See, in every time I am going to say you, I am going to compare it about zinc, cadmium, mercury. So you are going to get reasons why zinc, cadmium, mercury are not considered a transition element, so to say, even if it belongs to the group. Alright, that is the D block, even it belongs to that particular D block, even if it belongs to this transition series, but it is not considered. Clear? Now here in this graph, we are going to understand the ionization enthalpies. The ionization enthalpies, ionization energy of the D block elements lie between those of S block and P block, already we have said you. The first ionization enthalpy of transition elements of the first, second and third transition series, you can see it there on the screen. 3D, 4D and 5D, it has been shown there. 3D in dotted, 4D in what you can say, that is not the solid lines, it is the broken lines rather I should say, and 5D in solid lines. Alright, 3D in dotted lines, 4D in broken lines and 5D in solid lines. You can see there on the screen. So what you can find is that the ionization enthalpy of transition elements are quite high and lie between those of S block and P block. Alright, you can see that on the screen. The first ionization enthalpy increases with increase in atomic number across a given transition series, although increase is not very regular. You can see sometimes it increases, sometimes it decreases, because due to the presence of, that is, fully filled and half filled subshells. Where there is fully filled subshells, ionization enthalpy is more. Where there is half filled or partially filled, there is ionization enthalpy is quite less. So hence the increase is not gradually. Got it? Increase sometimes increases, sometimes decreases. Got it? You can see that for that particular reason. It's not very regular. It is irregular. The graph you can see that. Understood what the reason? I have told you the reason. Due to the presence of half filled and fully filled orbitals, which is quite stable, so ionization energy will be more in that cases. You've studied in class 11. Try to recollect that. Got it? And due to the presence of partially filled orbitals, ionization energy is quite less. So hence you will find an exception always in a graph on moving from left to right in a particular period. You will not find that is a regular graph. You will find sometimes increases, sometimes decreases. You have studied in lower classes in class 11. The first ionization enthalpy of the elements of the third transition series are higher than those of the elements of the first and second transition series. Alright, of the third transition series means the 5D series are quite higher than 4D and 3D series. Alright, you can see it there. Clear? The smaller the sum of all the ionization enthalpies needed for a transition metal to attain a particular oxidation state, greater is the stability of the compound. Alright, of that metal in that particular oxidation state. I think I should repeat once again. Smaller the sum of all the ionization enthalpies needed for a transition metal to attain a particular oxidation state, greater is the stability of the compound of that metal in that particular oxidation state. For example, nickel compounds are thermodynamically more stable than platinum compounds. Means nickel 2 compounds having oxidation number 2 is more stable than platinum compounds having the same oxidation number 2. Whereas platinum 4 compounds having oxidation number 4 compounds are more stable than nickel 4 compounds. Alright, the same reason it is. Alright, the same reason. What is that? Smaller the sum of all the ionization enthalpy needed for a transition metal to attain a particular oxidation state, greater is the stability of that metal in that particular oxidation state. Got it? So, so for that reason you find that K2PtCl6 is a well-known compound, whereas the corresponding nickel compound is not known to us. For that particular reason we can say that. Clear? So in this way, this is about your ionization enthalpies, which I said you about it. Now coming to the, what you can say, the oxidation state. If you see the oxidation state, then we can show the oxidation state here. That is about the oxidation state. Yeah, this one is oxidation state of the first row of transition metals. The common one is being showed in bold letters. We can say that. That is common one is +2, +3, +4, +5, +6. You can see in different one, and correspondingly the compounds I have given you at the what you can say at the bottom. So you can see here two that is tables you can see here. The first table shows the oxidation state of the various metals of the transitional elements. We can say that, and the most common one is showed in bold letters, and the correspondingly at the bottom another table is there which shows the compounds. Alright, acha. Now the most of the transition elements exhibit several oxidation state, except a few exceptions. We can say that. Got it? Except a few exceptions, we can say that the transition metals exhibit more than one oxidation state, and so variable valencies in their compounds. For example, copper exhibits an oxidation state of +1 in cuprous salt, while +2 in cupric salt. We can say that. Clear? So we have seen that earlier the electronic configuration of the transition elements is of the type n-1 d 1 to 10 and ns 1 to 2. n-1 d power is 1 to 10 and ns power is 1 to 2. The energies of n-1d orbitals and ns orbitals are very close energies of n-1d orbitals and ns orbitals, and there is not much difference in them. Therefore, in case of transition elements, both n-1d and ns orbitals are available for bond formation. Thus, the +1 and +2 oxidation state involve the participation of ns electrons, but higher oxidation states such as +3, +4 and +5 as well as +6 involve the use of n-1d electrons in addition to ns electron for the bond formation. Alright. So the most common oxidation state of elements belonging to the first transition series except scandium is +2, which arises from the loss of two 4s electrons. You can see there. You can see it on the screen. Got it? The elements belong to the first transition series except scandium. So the most common, you can see that scandium has got what? +3. You can see it on the screen. The bonds formed by transition metals in +2 and +3 oxidation states are mostly ionic. +2 and +3 are mostly ionic. On the other hand, the bond formed in the higher oxidation state are essentially covalent. That means all +2, +3 are ionic. And 4, 5, 6, 7 all are mostly covalent in nature. We can say that. Covalent in nature. Within a group, the maximum oxidation state increases with atomic number. Yes, you can see that as the atomic number increases, the oxidation state increases. Got it? So it is maximum in the middle, then after that again it decreases. Got it? You can see it on the table. See the table properly. I am saying all these things by looking at the table. All these things, what I am saying to you. So the highest oxidation state shown by any transition element is 8. Got it? Sorry, it is 7. We can say. Sorry, it is 7. We can say. So transition metals also forms compounds in low oxidation states such as +1 and 0. For example, oxidation state of nickel in nickel tetracarbonyl is 0. NiCO4. You have studied in coordination compounds. NiCO4. That is, CO is a neutral ligand. So it's nothing but it has got, that is 0 oxidation state. We can say that. So the more negative or less positive the value of E naught, Mn +/m, greater is the stability of the element in the +n oxidation state. Alright, this I studied about the electrode potential, which you studied in electrochemistry. More negative or less positive the value of E naught, means standard electrode potential of Mn +/m, greater is the stability of the element in +n oxidation state. For example, in case of copper, we have E naught Cu +/Cu as 0.52 volt, whereas E naught Cu2 +/Cu is 0.34 volt. Since the values of standard electrode potential for the electrode system Cu2 +/Cu is less positive than that for Cu +/Cu, Cu2 ion is more stable in aqueous solution than Cu ions. We can say that. Clear? So this is about your oxidation state, which I discussed with you. This I have said you. Got it? Now next is what you find is that they are generally that is paramagnetic as well as diamagnetic. Which one? That is transition elements. The transition metal ions have completely filled d orbitals or completely filled d orbitals. They are colorless. We can say that they are basically colorless. Got it? Clear? And most of the transition elements and many of the compounds show paramagnetic behavior. Got it? They are paramagnetic behavior they have. Got it? So this is due to the presence of unpaired electrons in n-1 d orbitals. As the number of unpaired electrons increases from 1 to 5 on moving from left to right in a transition series, the paramagnetic characteristics of transition metal ions increases. The maximum paramagnetism is found in the middle of the series. Why? Because in the middle of the series we have got maximum number of unpaired electrons. Moving further, the magnetic behavior decreases with the decrease in the number of unpaired electrons, because as you move d6, d7, d8, d9, they are all paired. They are having more number of paired electrons than unpaired electrons. Got it? The transition metals or ions having paired electrons show diamagnetic behavior. We can say that. So except for mercury, which is liquid, all the transition elements have typically metallic structure, HCP, CCP or BCC. They exhibit all the characteristics of metals, that is, they are hard, lustrous, malleable, ductile and have high melting and boiling point, and have high thermal and electrical conductivity and have high tensile strength, so to say. So this I have discussed with you, that is about the melting point. About this also I have discussed. This also I have discussed with you, that is about the this energies. This is your ionization energy. I am showing you the catalytic properties. If you see, the catalytic property of transition elements are probably due to the presence of unpaired electrons in the completely filled d orbitals, and hence possess the capacity to absorb and re-emit wide range of energy. This makes the required energy of activation available. We can say that the most of the transition metals and their compounds, particularly oxides, act as a catalyst for a number of chemical reactions like iron, cobalt, nickel, platinum, chromium, manganese. They are the commonly used catalysts. We can say that. The catalytic activity is due to presence of vacant d orbitals. You may note it down. The presence of vacant d orbitals due to the tendency to form complexes and due to the ability to exhibit variable oxidation state. Again I say the catalytic activity of the transition metals and their compounds may be attributed to the following factors, which is the presence of vacant d orbitals, ability to exhibit variable oxidation state, and tendency to form complexes. And transition metal ions form a large number of complex compounds, and the large number of complex compounds is due to small size, due to high nuclear charge, and due to the availability of vacant d orbitals. Got it? The tendency to form complexes also is due to what you can say small size, due to high nuclear charge, and due to the availability of vacant d orbitals. Now they also form interstitial compounds. Transition metals on the screen you can see form a large number of interstitial compounds in which small atoms such as hydrogen, carbon and nitrogen occupy the empty spaces. Interstitial means there is an empty space in the lattice structure, the empty space which is there between the two atoms. There the smaller atoms can come and occupy and form interstitial compounds. So interstitial compounds basically have some properties, some characteristic properties. Their melting points of these compounds are quite high, higher than those of the pure metals. Interstitial compounds are very hard. They exhibit conductivity similar to that of pure metal, and they are chemically inert in nature, we can say that. Now d block elements also have got a tendency to form alloys. The transition metals form a number of alloys among themselves. These alloys are hard and often have high melting points. The tendency of transition metals to form alloys among themselves may be attributed to the fact that their atomic sizes are very similar. Noted this point. The tendency of the transition metals to form alloys among themselves may be attributed to the fact that their atomic sizes are very similar. For that reason they form alloys, we can say that. Alright. So this is about what you can say your transition elements in the first part I have said you. Okay, thank you.